This is an overview of all the research I performed during my PhD under the title Numerical Modeling of Heat Treatment and Post-Processing Following Additive Manufacturing of Metal Parts. So everything will be framed in terms of the length scales that are relevant for numerical modeling, the microscale being the smallest scale, which is mostly concerned with the microstructure of the metal. The mesoscale allows us, because it is larger, to include fluid dynamics, while the macroscale is mostly concerned with residual stresses and the effect they have on the part. I have developed two models at the macroscale. One is a simplified approach capable of seeing the effect of the order of the post-processing operations, while the second one shows the effect of dwell time and heat treatment temperature. The third model is a microstructural model for a heat treatment above the beta transist temperature, while the fourth model investigates a one-way coupling scheme between mesoscale and microscale, while the final model is a two-way coupling between microstructure and macrostructure. So going on to the results from the first model. So there are two different process chains being evaluated. At the top you can see the beam first being cut from the base plate and next heat treated, while on the bottom the reverse happens. It is first heat treated and then cut from the base plate. If we look at the residual stresses just before the post-process happen, we see the expected tension at the top of the beam and compression at the bottom. This results in bending of the beam, and we can clearly see the effect of the order of the post-processes, with the beam being heat treated first, bending significantly less. Moving on to model 2. This is the stress field that is used as an input for the heat treatment simulation, which was validated using actual experimental measurements. After the heat treatment, the residual stresses are significantly lower. If I can focus your attention for one moment on the scale bar on the right, you can see that the residual stresses are 2 orders of magnitude smaller, approximately. This simulation was used for a parametric study with 5 different heat treatment temperatures and 6 different heat treatment times, which shows that the model is capable of showing that the residual stresses reduce for higher temperatures and longer times. And then finally, all of these results were used as an input for a process map, which can be a handy tool for determining rapidly the optimal heat treatment given certain boundary conditions. The microstructural model starts with a micrograph from which I extracted an initial microstructure for the simulation. At the end of the first half of the simulation, so at the heat treatment temperature, you can see the transition to aqueous beta grains, and then to the right of that there is the final microstructure at room temperature after cooling down, which exhibits both Wittmann-Stettin and basket weave lath structures. This was validated by first comparing with an actual microstructure of a part undergoing the same heat treatment, and also by comparing the grain diameters of this real micrograph with the aqueous beta grains at the high temperature. Both of these distributions are log normal with similar average and standard deviations. The next model explores a one-way coupling scheme between mesoscale fluid dynamics and microstructure. So at the top left you can see the results from the fluid dynamics simulation, which were used as an input on the process map to the bottom of that. And this process map shows that the entire microstructure is columnar. This columnar microstructure was then used as an input for the microstructural simulation, resulting in the evolution from columnar to aqueous you can see on the right of this slide. Finally, there is a two-way coupling model from which couples microstructure through a JMAC-based equation with a microstructural simulation. And this is a first figure of the microstructural evolution in the last layer that is deposited. So you can first see a peak in the beta phase fraction as the layer itself is put down, and then the evolution of the alpha phase fraction. Next, there is the evolution of the microstructure at the layer that was deposited first, and here you can see the effect of the intrinsic heat treatment, with the first peak in the beta fraction being caused by the layer itself being deposited and the subsequent ones by layers above it. Unfortunately, the effect of the microstructure on the residual stresses is fairly limited. During my PhD, I contributed, at least in part, to these 8 publications. And then to wrap up, my thesis had the title Numerical Modeling and Heat Treatment of Heat Treatment and Post-Processing Following Additive Manufacturing of Metal Parts. It started on the 1st of September 2017. I submitted my thesis on the last day of August 2020 and defended on the 15th of October. Thank you for your attention. And